now I'd like to introduce James Dunlop from the Carbon Trust.
Thanks, Susan, and good morning, ladies and gentlemen. Yes, my name's James Dunlop. I'm a senior engineer with the Carbon Trust, and today we're going to go through our Green Business Fund technical webinar on motors and drives. So just to give you a flavour of what we're going to cover, we're going to look at a range of topics on motors and drives. We're going to give an overview of technology, look at opportunities for savings, examine the benefits of using variable speed drives or VSDs, look at motor efficiency and motor efficiency classification more generally, and also look at motor management policies. So this webinar should give you an overview of the motor types and their applications, look at these opportunities for savings on motor systems, and provide a practical understanding of motor management policies, as well as referring back through to case studies to see what has been carried out by others in terms of motor efficiency, and look at ways to assess the condition of current motor stock and to understand how energy performance can be improved. And I think that the point at the bottom there really is the important point to remember, and that is that in a single year the running cost of a motor is often up to 10 times its purchase cost. So whilst you might be buying a motor at a few £100, the energy that goes through that motor during its life is far more significant, and it takes a whole life costed approach whenever it comes to motor selection. So just to give you a bit of background on the Carbon Trust, we are a not-for-profit organisation with a mission to accelerate the move to a sustainable low-carbon economy. We do that in a number of ways. We provide advice to businesses, governments and the public sector on opportunities for energy efficiency and low-carbon technology. And the Green Business Fund is one of the schemes that we provide that advice through. It's been operating for a number of years now and has been run by Carbon Trust staff. We also provide footprinting to measure and certify the environmental footprint of organisations, products and services, and we also help to develop and deploy new low carbon technologies and solutions. So looking now at motor technology in particular, and it's important just to emphasize the significance of electric motors on electricity consumption. So globally, electric motors are estimated to account for 40% of all electricity consumption. And if we look at the UK in particular, and looking at UK industry, electric motors are estimated to account for in around 2/3 of the entire industrial electricity consumption. So they're a big part of the energy mix for companies in the UK, and obviously they're embedded into a range of different systems across processes, across air handling and air conditioning systems, compressed air, and a whole range of technologies. So electric motors are a broad church. There's a very wide variety of electric motors out there. The main types that you'll find in industry tend to be in this category here: the induction motors, single phase or three phase alternating current motors. So that's often the case whenever we're talking about electric motors. We're mostly talking about those induction motors. There are DC motors out there, direct current motors, which are used widely in heavy industry, and more recently technology has come in for brushless electronically commutated motors, which can be used efficiently in many applications, and we'll come on to that later. So there's more information on electric motors within our Carbon Trust guidance as well, if you want a more in-depth look at motor technology there. But looking at the basic characteristics, a lot of that can be picked up from the nameplate of the motor. So you can see there on the right, we have in the photograph at the bottom a picture taken of a motor nameplate. You can see there quite clearly that the manufacturer there, it's Flackwoods, and you can also see the motor efficiency classification that we'll come on to. It's listed as IE2. The rest is probably quite hard to read given the scale of the photograph, but looking at the image above that, in terms of the standardized nameplate, you can see there the information that you're going to pick up. You're going to pick up information on voltage, whether it's single phase 230 or three phase 400 volts. You're also going to pick up on the kilowatt output. You can see in that example it's listed there as 15 kilowatts. The speed will be listed in RPM, and there'll be some information on the motor design in terms of the number of poles often, which comes down to the setup of the motor and its speed. Other useful information, as we say, there is the efficiency class. So picking up on the standard efficiency of your existing motors will be important, and you can do that by looking at the nameplates. And also other information that would be pertinent would be the date of manufacture, to give an idea as to the age and the opportunity to replace the motor. And again, just to a wider point, motors are rarely used in isolation, so it's worth examining what motors are being used for, what their requirements are, and they're often part of a much larger system. So it's worth looking at what the system is doing and not just what the motor is doing. And often it can be the case that motors will be integrated into a system with the use of electronic drives, with transmission systems, and with other drive equipment. So you can see here in this graphic that there's losses along the line here. You can see drive losses there of in around 5%, potentially motor losses of 8% or more. You can see further losses in the transmission. The example there is a belt-driven transmission system, which is showing transfer losses of in around 10%. So the use of direct drive motors and the likes can avoid those transmission losses and can provide savings. And then there can be losses whenever it comes to the actual use of equipment, whenever it comes to, say, fan use. So all of that adds up to significant losses, even if you have a relatively efficient motor within the middle of the system. So again, it's worth looking at the overall picture with regard to the system rather than just the motor itself. So where can we find the savings then? Well, basically, there are some very simple things to do first before you examine opportunities to replace equipment. Firstly, looking at your switch off policy. Looking at when motors can be switched off is important. Manual switch off is obviously the easiest way to do this, but it's important to have procedures in place to make sure that can be done safely and without any risk to personnel or to equipment. Automatic switch off can be beneficial where you're looking at conveyor systems and the likes, using load sensing devices perhaps to switch off the motors automatically. Then looking at your process more generally, looking at set points. If it's a HVAC system, a heating system, potentially you might be looking to reduce temperature set points. Same thing would apply for refrigeration. You may look to perhaps increase temperature set points there. With compressed air, you might look to reduce the pressure overall to reduce the demand on the motor. The other thing to consider would be to change the loading of the motor to look at different running periods to achieve the same thing and to operate more effectively. And then overall, as we talked about, looking at system design and optimization, so looking at what can be done differently within your processes to minimize the work on the motor. With regard to the motors themselves, we're going to look in more detail in the next section at variable speed drives, and that's a key opportunity for savings. So adjusting the speed of the motor to match the demand set on it by the system will be important, and that can be applied well to fans, pumps, compressors, conveyors, etc. And it also provides additional process control and options to improve your process more generally. Soft starters are often mentioned with regard to motors. They can reduce that initial starting current and that can help to extend motor life. In energy terms, that's really a very short transient period as the motor starts up, so it will provide an improvement to the startup, but won't provide the same level of energy savings as the other measures we're discussing here. And then the last point there that we'll come on to later in more detail is looking at the motor efficiency. So looking at that efficiency classification of the motor and having a policy in place to replace your motors with the most efficient types available will provide long-term savings. Also, other things that can be considered, you can avoid lightly loading motors. Motors tend to operate most efficiently whenever they're operating above 50% and in around 75 to 90% of loading. It can often be the case that motors are oversized initially at the design stage. They'll be put in to make sure they're able to handle the capacity, but if they're oversized for the function they're providing, they could well be operating at lower efficiency levels. Also, we mentioned it earlier, the use of belt drives that can deteriorate with age. You can see a reduction in efficiency with poor maintenance. So keeping those well maintained, keeping them aligned and keeping the standard of the belts to a high level can improve efficiencies. And I suppose more generally, as we say in the bottom point there, the use of direct drive motors would eliminate the need for those belts, thus improving efficiency, and that can be applied well to the likes of fan systems. Where gearboxes are required, again, the different types of gearboxes will have different efficiency levels. So applying the right type of gearbox to the right application will be key there. So we're just going to look in a bit more detail at the use of variable speed drives in this section. So in terms of what a variable speed drive does, it essentially converts the incoming electrical supply of fixed frequency and voltage into a variable frequency and voltage. So you'll be getting 50 hertz and 400 volts at 3-phase in. To control the speed of the motor, you'll want to change that frequency, which will change the speed of the motor, and you also have the ability there to change the voltage as well. So it's essentially a piece of power electronics that enables that control of the motor. And the real benefit in doing that is that you can adjust the speed and torque as needed to match your system. So motor speed can be varied from 0 up beyond the full rated speed of the motor. And in doing that, what you can see is the ability to match torque with the requirements, and it's particularly effective where you have applications which require variable speed or variable torque. So that relationship between power and speed, in simple terms, the more speed, the more power provided. Reducing the speed can reduce the power requirements. We'll come on to that shortly in a couple of slides as to the differences there is between different loads there. And speed reduction can make significant savings, especially when it's applied to the likes of fan systems, pumps and compressors. And the amount saved depends on the reduction possible, and that's not going to apply to every application. But essentially, where you want to have that change in speed, you'll need to have a variable speed drive, or an inverter as it's often called, to control that speed intelligently. And as I say, that's really examining the saving that you'll see from different load types. So if we look firstly at the line in red along the bottom for constant power, you're not going to see savings there. So you have a need for constant power from a motor system. The variable speed drive won't provide savings. It'll need to provide the rated output constantly. Where you have constant torque loads, there is the opportunity for savings, as can be seen there in the orange line. And so speed can be reduced to provide savings. And where you get the highest savings is with variable torque systems. And as the speed reduces, you can see here that you're getting significant levels of energy savings from operating at lower speeds. And looking at applications of that, the chart on the left looks at pump systems. You can see what would happen normally on the line on the top here. So that would be with a fixed speed power input to a motor, you're going to see a slight change in motor power in relation to flow rate. But the lower graph looks at what happens with a variable speed drive. So you're seeing there that it's a much lower level of power required for the delivery of the rated level of flow there, and that essentially gives significant savings, and that's shown here in this graph by this area here effectively. So that's the amount of power saved between the differences in approach from a fixed speed system to a variable speed system. And again, that will apply where you have a need to vary the flow rate. So if your flow rate is fixed, then it's a different story. But here, where the flow rate is varying, the use of a variable speed drive will make significant savings. Similarly, if we look at fan systems here on the right, you can see what would happen with a fixed speed motor running the fan system. So a little bit of a saving from damper control, but what will happen with a variable speed drive is that the fan will be much better able to match the flow rate required. And as that flow rate requirement reduces, you can see here that there's significant reductions in the power input required. So very, very effective in those scenarios where you have variable flow rate. And then if we look then as to the level of savings here, where we have a fixed speed pump, and this example, we're considering an existing fixed speed pump of 22 kilowatts operating for 6,000 hours per annum. So it'll have an absorbed power of in around 15 kilowatts. It'll run constantly at a speed of 1450 RPM, and as a result of that, it'll consume 90,000, just over 90,000 kilowatt hours a year at a cost of in around £8,000 per year. So if we look at the requirements of the system, and we assume that it has a requirement to operate at full power output for 40% of the time, and at a reduced power output for 60% of the time, it has the option then to operate at its full absorbed power at 15 kilowatts for some of the time, but then sit right back to just 6.4 kilowatts for 60% of the time. And that is through the reduction in speed. So you can see there that it's reducing its speed to just under 1100 RPM. And that'll make a significant difference in energy use. You can see here the energy required in this scenario is then around 60,000 kilowatt hours per year, and that means that it's going to operate with a running cost of about £5,300. So for this scenario, we'd estimate you might need to spend about £4,000 on a variable speed drive. That'll generate savings of 2,800 per year, the difference between the two running costs there, and give you an effective payback of 1.4 years. So that would be a fairly typical example of the application of a variable speed drive, and you can see there that the financials are very attractive. And that's borne out by some of the case studies that we've seen over the years. The top example there is on compressed air, with a manufacturing company replacing a 22 kilowatt fixed speed compressor with a 30 kilowatt variable speed compressor. So in terms of their investment there, they'll have invested in the replacement of the whole compressor system at a cost of £10,000, but that'll have seen savings of in around £4,000 per year, giving a payback period of less than 3 years. So again, it's very attractive, and that'll have been informed by a study as to the flow rate required at their site. So they'll have investigated the level of compressed air demand. Often that varies depending on operations across the working day or working week. So in their case, the use of a variable speed drive will have been able to give effective savings. In the second example there, we're looking at a fan application. So a glass manufacturing company was able to equip two very large 200 kilowatt motor fans with an inverter at a cost of £43,000. That saw savings of £36,000, giving a payback of just 1.2 years. And that, I suppose, would be an ideal application of the technology if we think back to the previous charts on fans and on fan speed. You're going to see significant savings in using a variable speed drive in that scenario. Okay, so that's most things covered on variable speed drives. Looking then at motor efficiency. Motor efficiency classifications we picked up on the early charts, and basically these have come through in recent years. They're listed in terms of their IEC energy classification from IE1 to IE5. With IE1 being a standard efficiency, and IE3 premium efficiency, IE4 super premium efficiency. Ultra premium efficiency at IE5 has come in relatively recently, so there'll be limited product availability in that area, but there are more and more motor systems coming through with higher efficiency standards. So essentially, if we look at what would happen with a 4.5 kilowatt motor with the line in red here, essentially you would be looking at an efficiency for an IE1 motor of in around 85%, that sort of level. We then move into the higher efficiency classes of IE3 and IE4. That brings the efficiency level up to 90% and beyond. So if you have a motor that's running significant hours, and again, if it's of a significant size, it's well worth looking towards the highest efficiency class possible. And a lot of the influence in terms of motor standards has come through from EU eco-design requirements, and they have pushed up the standard for motor efficiency classifications over recent years. So essentially, since 2011, the minimum standard for motors from 0.75 kilowatts right up to 375 kilowatts has been IE2. You may well have older IE1 motors in place from before that date, but that has moved the bar up a little. And then from 2015, the requirement has been for IE3 motors for general use, or if they are equipped with a variable speed drive, they could be IE2. Now at that time, that just applied to motors greater than 7.5 kilowatts in size. So there'll be a lot of smaller motors that wouldn't have been impacted by that requirement in 2015. But then in January 2017, the requirement was then broadened. Same principle, IE3 generally, and IE2 if equipped with variable speed drives. But in this case, it went right down to the smaller motor sizes at 0.75 of a kilowatt. So replacing motors with higher efficiency versions saves energy. It may cost a little more to purchase the highest efficiency classes, but if you see a saving of even 2 to 5%, that'll have a significant whole life benefit to the motor costing, and you'll see that additional investment return to you. So it's important to look at that probably whenever it comes to this point of motor replacement. That often can be the case when the motor fails, and it's worth looking at the options as to whether to repair or to replace at that stage. So if we think about an 11 kilowatt higher efficiency IE3 motor, it'll use almost £250 less per year than a lower efficiency IE1 motor. So there's significant differences between the cost of operating the different classifications of motors. And often with this type of investment, it's not a case of going out and ripping out all of your older, less efficient motors, but having a policy in place which informs future purchasing decisions to ensure that you're going with the most efficient options available to you. And in terms of where these improvements have come from, there has been significant gains in motor efficiency over recent years. This chart's taken from the International Energy Agency from back in 2011, and this is looking at areas that could be improved on at that point. So the use of the active materials within the motor design, the way they're set up, and the quality of the materials used can have a significant impact. And just the improved design and geometry of the layout of the motors will provide savings too. And overall, all these small improvements have led to significant gains on motor efficiency, and that is continuing. So it's I suppose it's a moving picture, and it's worth keeping on top of. So just to look at an example as to what your options are if a motor fails, what do you do next? What are the best options for you? So in this example, we're thinking about what would happen if your IE1 motor failed. You could rewind it for a cost of £800, or you could purchase a new high efficiency IE3 motor, but that would in turn cost significantly more there at £3,000. So we're looking at a 37 kilowatt motor. it would be operating with an efficiency of in around 88% for the sake of this example, compared to 93.6% for an IE3 motor. You can see there the difference in running cost. You're paying in around 19,700 for the IE1 motor, in around 18,500 for the IE3 motor, which is operating at improved efficiency there. So the annual cost savings are in around £1,200, but you're having to pay a higher immediate cost of in around £2,200. The difference there between rewinding and replacing. So what do you do? Well, looking at that over a 10-year lifetime, you've got that additional cost of £2,200, but you're seeing annual cost savings of just under £1,200. So you're seeing that every year as the life cycle of the motor continues. So you'll be out your £2,200 in the year zero, and then going through the following years you'll start to recoup that, and by the end of the 10-year life with a 4% energy inflation rate, you'll see a positive cash flow of close to £12,000. So over the lifetime, you're seeing a rewind motor cost you $236,000 in terms of its rewind cost plus its energy use, compared to a lower figure there for the IE3 motor. So that lifetime saving, assuming a short 10-year life in this case, is £12,000. So that's the sort of difference that it's worth looking at. So it's worth looking at what your policy is when it comes to rewinding or replacing motors. And in some circumstances, the technology changes are more significant. This would be the case for electronically commutated fans. So the legacy motor technology in this case, in terms of shaded pole motors, as you can see there in the image in the center, was particularly bad. So there's a significant difference in terms of the energy performance of the old technology compared to the newer technology in terms of the EC fan shown on the right. So it's a slightly different technology, as we mentioned earlier in the presentation. It's operating with a DC motor, and it's operating with brushless technology, able to operate more efficiently. What we're seeing for the likes of a refrigeration cabinet, as is the example here, is that you're able to replace a single shaded pole fan operating at 24 watts with a EC fan operating at just 7 watts. So the cost there for a large scale rollout would be in around the cost saving there per fan would be in around £24, and for a large scale rollout you're going to see a payback of 2 to 3 years in doing that. And again, this was the other opportunity, if you are looking at refrigeration systems in particular, would be to make sure that that type of technology is specified in your new cabinets, and that's becoming more and more common these days. So that could be an example where it'd be worth looking at actively replacing based on the efficiency standard of the motor. And I suppose more generally, as we're going to come on to now, the best way to address that is through your motor management policies. So the motor management policy is aimed at providing a structured approach to the repair and maintenance of motors. So it should look at a schedule and procedure for motor maintenance firstly. It should also look, as we've talked about, a plan for purchasing new and more efficient motors, and as well as that, where there are options to repair failed motors, when should they be repaired and when should they be replaced. And it'd also be useful to track there the number of times that motors have been repaired or indeed rewound. So your motor inventory would form the basis of your information for that. So that will be the starting point as to the existing motors that you have in place. So that can provide a framework to track the motors that you have and to record any performance information. So you can see there in the example on the right, the level of detail that would be in there in terms of the reference information for the motor, the nameplate details as to the function and the efficiency class of the motor, the equipment details as to what the motor is doing, any repair history in terms of what has been carried out to repair the motor. And I think probably the most important thing there is really then the action. When that motor next fails, the action could be to replace it with an IE3 motor. And again, given that it's operating a pumping system, it could be worth looking to see if a variable speed drive would be suitable as well. So having that inventory built into a policy will mean that once that particular pump motor fails, that somebody picks up the inventory, sees what the status of the motor is, and makes the best decision in terms of purchasing the most efficient motor to replace it, rather than simply replacing like for like or looking at the cheapest motor available at that point. And in terms of maintenance, I suppose it's worth as well just checking the standard of motors, looking visually at the gearboxes for any issues in terms of leaks or damage, regular cleaning, looking at belt tensioning where you have belts in place, looking at alignment checks on the belts, motor temperature, any unusual noises, and carrying out that day-to-day maintenance. That will also form part of your motor management policy. And again, come back then to that decision as to whether to repair or replace motors. It's often the case that that'll be based on the life cycle costing, as we looked at earlier. So where you have smaller motor sizes, especially where they're running for long hours, the decision is probably going to be straightforward to replace them. By exception, perhaps for much larger motors or where the motors are operating for short hours, it may be prudent to repair them. But again, that'll take closer examination. And it's also worth bearing in mind there that you'll see an efficiency drop of in around 2% once the motor is rewound a couple of times. So in terms of procurement then, I suppose it's worth emphasising that it's worth embedding this whole life costing approach into your motor procurement practices, and that should make sure that you're moving towards the higher efficiency classes at minimum, as we can see there from regulation of IE3, or preferably beyond that you're examining where the opportunities are to make best use of variable speed drives, and also that there's clear guidance as to whether motors should be repaired or replaced. And then again, as with all the work we carried out, it's worth looking at getting best value for money, looking at whether your arrangements with a preferred supplier or potentially a tender might give you the best value for money overall. Okay, well that concludes the technical aspect of the presentation. I'll just go through some details now on the Green Business Fund. So the Green Business Fund is a scheme operated by the Carbon Trust to contribute to improved sustainability and energy efficiency. It applies to SMEs in England and Wales, and the programme provides a combination of advice and training on energy efficiency. So in terms of who is eligible, it's eligible to SMEs. It's also available to schools, sole traders and charities. And in terms of our definition of SMEs, you can see it there on the right. So if you meet those criteria in terms of employees and in terms of the financials, then you'll be eligible as an SME to apply. So we provide a number of strands of support. The first of them there is our workshops. You can see there a schedule of workshops coming up through May and June across the country. And these are typically 2-hour long workshops delivered by the Carbon Trust, and they can help you understand energy consumption and identify savings for your business. We also provide opportunity assessments, either remotely for smaller companies with lower energy spends, or directly on site for companies with higher energy spends. They're delivered by Carbon Trust engineers, and we try to focus in on the top 3 costed energy saving recommendations across whichever technologies are applicable. We also provide implementation advice that helps you match up with suppliers. We'll also provide support for you if you want to run tenders to review proposals, and that's available again to SMEs. We run technical webinars such as this one. We have a range scheduled across the coming months, and there's also a wide resource of publications on our website covering a range of technologies. There's information there on motors and drives in particular. And we also provide a range of tools to help you measure your carbon footprint, to benchmark your energy use, and also to build the business case for lighting upgrades in particular. So that concludes things from me. Just going to check now with Susan to see if we have any questions.
Yeah, so we'll just give it a minute here and just see if anyone has any questions, send them along, and I will read them out shortly. Okay, James, we do have a question here. The question is, what about switched reluctance motors? What are your views on this?
Well, I suppose that'd be a fairly niche technology, probably worth discussing offline if it was of relevant. On that, I mean, I think what we saw from the initial slide there, if I just go back to it, was that there's a very wide range of motor technologies available out there. So what we're looking at primarily is the efficiency standards around AC induction motors, but certainly where it's worth looking at other technologies which provide different approaches, then that's worthwhile. We mentioned that in terms of EC motors, in terms of permanent magnet motors, and the same principles would apply really to switch reluctance as well.
Okay, another question here. Do you have any best practice to share on energy savings for compressors?
We do have good compressed air guidance on our website. So there's a bespoke publication on compressed air that'll look at the opportunity for higher efficiency compressors for variable speed drive use on compressed air. And I'll also look at a range of other issues in terms of air leak detection and repair, looking at heat recovery, and also looking at other maintenance improvements and other improvements to the use of compressed air. So it's worth looking at that publication on that in particular.
Okay, so I think that's all the questions we have for now. If anyone else thinks of any additional questions, just feel free to send them along. When we send out the slides, you can reply to that. So thanks, James, and thanks everyone for attending, and that will be the end of the webinar.